collecting, provide high-quality databases and data sets, and making that useful to the community. Really, where we've been evolving is at the level of providing a highly distributed software infrastructure. The capability to begin to tie that together across distributed data repositories and be able to really tie it together internationally. Parts of PDS, and you'll hear us talk about, a lot about this in my conversation, my talk, also in Steve Hughes' talk, is a planetary science information model. Diversity of planetary science. We'll say that there's, say, 4,000 different types of objects in PDS. It's really, really difficult for us to not have a well-defined way in which we understand the interrelationships between the data that goes into the archive. Captured approximately a petabyte of data. We're actually a little higher than that now. Heard us talk about the IPDA, the International Planetary Data Alliance, from back in 2007, really to begin looking at how we not only are bringing the data together within the context of NASA, but we're internationalizing that around the world to bring our partners together. And it's great to see so many of our international partners here at this meeting, because that's really been our goal, is to look at how do we worldwide planetary data environment. So the PDS, one of the things you do know about it is we are a distributed system. You see that up in the upper right. I won't show dive in that, but this just describes or shows kind of the composition of the PDS, and the fact that we are a distributed archive, and we've got to address that as part of how we actually implement PDS4. So some of the key drivers that really have been affecting PDS. One is more data. That's something that's happening across all science areas, and so you hear this notion of big data, so forth. In many ways, I think PDS is in good shape to be able to address some of those. I'll show you kind of the trend line of what's happened over the last decade of PDS. Other things we're seeing, though, is more complexity in our data. We have more complex data products. We've got to be able to describe those data products. They're coming from other various types of instruments, and so those present challenges to us. More producer interfaces. We fly well over 100 different instruments that are delivering data to PDS. So we've got to be able to deal with those kinds of cases, as well as new types of and new types of ways in which we're going to get data. So that's going to be things like the DAP programs and so forth, which are delivering data to PDS. Greater user expectations. This is something that we've seen in the PDS more and more, particularly. We've got a crop of graduate students and others that really are savvy to being able to use Python and R, MATLAB, and build some good data. And I think we're going to see a lot more of that in the future. So we want to be prepared to be able to services in ways in which users can exploit and work with our data. Challenge for us. We've got this diversity usability. How do we balance this question of long-term preservation? Our data is usable in 50 years. I think I hear that we still sometimes use Viking for land on Mars as valuable data sets, and so we want to make sure our data is useful in 50 years. And that competes sometimes with trying to put data into contemporary formats. As part of its for architecture, has this notion of not only being able to preserve data in stable archive structures, which will also be able to transform that data so they can be used in modern tools. We'd like to do everything, but we do have funding constraints. We're looking at this idea of moving towards more and more of an integrated but federated system. A lot of drivers on internationalization, as I've mentioned. And one of the things that we're dealing with is just the realization that as we are running a petascale distributed archive, we realize, and so we're dealing with them to provide ways in which we're secure as a system for access. And so we sort of balance those kinds of tensions. And then last is technology opportunities. Before, a lot of the things we put in there were hooks recognize that there are emerging capabilities in areas like data science and big data and station and so forth that really can help us provide better ways to scale the PDS, to be able to provide better access, to be able to provide better interaction working with the data. And so you'll see this quote at the bottom came from the NRC as part of their decadal survey. A real strong statement to say that we need to support the ongoing efforts to evolve the planetary data system from an archive facility, so that's capturing the data, to really be an effective online resource for NASA and the international community. And that's really our goal, is to look at that evolution and where we're going over the next decade. The growth of what we've seen in planetary science. So we were worried back in 2001 when we were getting off the CD and DVD. At that time, we were about 4 terabytes of data. Today, we're well over a petabyte. You really see this increasing scale. And I think that these played a big role in helping us move towards this kind of a scalable architecture to be able to handle the ability to capture and distribute this data. So we actually distribute well over 100 terabytes of data from PDS a year. So there's quite a bit of data that are moving in are moving out of PDS for being used. We're seeing PDS every year now. So PDS is really scaled to be able to support a lot of the basic infrastructure needs to be able to ingest and distribute the data from the community. The diversity of data, we've got about 2,000 data sets in PDS. One of the things I find interesting is, for instance, with, say, Earth Science and NASA, we've got about 600 instruments we brought. And that's an interesting example. Earth Science has, I think we've seen about 300-ish instruments, but they've got a lot more data. So if you look at what PDS is dealing with, the planetary community, it might not be volume size so much in terms of Earth Science, since we've got certain kinds of constraints in terms of getting our data back. We certainly are dealing with the diversity of data, and that's what you see here when you see the various kinds of targets we've got to look at, the types of data we've got to capture, and so forth. So as we built PDS-4, the idea was to really drive an architecture, so I'll use that word, that was driven by our information model. The reason that we did that is that we can take and we can configure our information model to describe the diversity. Yeah, and that was something that we recognized when we built PDS-3 and others, that we had actually listed the model, but it wasn't actually documented in a way that could drive our systems. And so we're making changes to PDS. Things would invariably break if you didn't understand the interrelationships of the data. And so PDS-4, a strong engineering approach to describe and use that. So we got this ability now to describe the diversity of data and really be able to drive software to help us manage search and drive analysis of our data. So where we're heading is the ability to really PDS-4 as that way to create this effective online infrastructure, a way to work with planetary data. That model then drives our service architecture to configure our software services to work with planetary data. And that's helped us in the context of moving to an international platform, because what we've actually begun to describe is a consistent way in which we can, and compatible way we can describe our planetary data, and then we can deliver and provide access and be able to exchange and share data through a common services software infrastructure. So just a little bit deeper dive on the PDS-4 information model, and like I said, you'll hear a whole talk on that coming after this one. Really key in terms of how we're building PDS-4. As I mentioned, it describes the relationships. So we understand instrument rights to the data, which we understand happening, and then invest. So all that's just information model. That's important for us to properly describe objects, information objects, which go in, and those go in as products. So we've got a whole draft out of information model to describe the organization, the curricular data in the PDS. The other thing that provides us is a guide for PDS. That can be a rough word here. In terms of what it allows us to do in the community, it's a very good word because it separates the field and people. It allows you to extend so the community can build their appropriate extensions. And that's allowed us to provide a way in which we can start to provide extensions at the various discipline nodes and so forth. And it provides us a way to think about or to work towards evolving PDS in the future. Information models allows us to add and easily accommodate new instruments, observations, and data, and to provide a structure for doing that. So we've got now a way to evolve PDS4 as we go back and address some of those drivers I mentioned, which are new types of instruments, more complex instruments, so forth. We can handle that in PDS4. Now, one of the things that we have done in PS4 as well, over having this governance model, as part of our common part of that model, is put that under configuration control. So we have a change control board that looks at every change. And the intention there is not to have that board be a design board, but to really be a gate to make sure we don't break things in the community. PDS is actually being used, and so it has representations both from the PDS nodes as well as from the IPDA. I won't spend a lot of time here, but we were asked once we had laid out this architecture and shown this to look at whether we could also do this at a NASA level. The idea is that I like of this picture is that it shows on the upper part of the diagram the whole idea of the information model. And so you see describing objects information, providing different levels of description of that. So we can go down to missions. In our cases, we can go down to instruments and add extensions. But below that is really the software architecture. So we're taking the model and we're driving and configuring software components which help us be able to understand how to work with planetary data. So that diagram, this diagram is very important to us because it gives us a strategy to work with and use data. So in PDS3 tools, we have a lot of different ways in which we parse data. Now what we want to do is a way in which we can actually work with our data so that we can be consistent across all of our kinds of tools we build. Part of the way that we're ensuring that this comes together is that we can go through a series of system builds. We take and we bring together the core model and the software, and we verify through regression testing that we haven't broken anything. Software works with the model, and we go through and make sure that we can validate a set of test cases. That's important to us to provide a consistent, stable platform, because what we view our job is to release this to the community. And so we're really co-developing PDS in many ways with the community, PS4, and we want to make sure that that's stable and also the releases are predictable. So each bill, as I mentioned, goes through this full cycle. The latest release was version 1.8, and that was released in April 2017. One of the things that we've seen through these release process over time, which is probably no surprise, is that the number of issues, the number of what we call SCRs, so standard change requests, have dropped dramatically because we've been able to really think about how this is coming together. It shows some of the core software standards. So we've got services, various tools, release all the various standards, which are the minimums and so forth. That's available online here at the PS4 website. This just shows our governance approach, where what we're doing in the middle is very rigorous baseline for PS4, but it allows for the community to build extensions of tools for software and also extend the information model. Things I'll point out, you might have seen a poster in the foyer, is we do have a tools registry. We've got about 60 tools registered. If you have tools you think should be available to the planetary community, check out the the website, see the poster, see Sean Hardwick, Sean, and he will get you registered. Just to keep us on time, one of the things we've seen is just a a dramatic adoption of PDS4 internationally as well. So we've got about 12 missions that are now using PS4, implementing PS4, and so forth. That's continuing to increase. We've got a number of other DAP programs that are using PDS. So really, as a community, we've moved to this internationally. And the other thing that we've actually put in place now is the ability to, as an international platform, start to search and access data from the various agencies. And so NASA and ESA have gotten together. We built a search service. If you're familiar with Apache Solr, we use Solr as a way to index and crawl and build a scalable search engine that can look across ESA and NASA data archives now. And we're working toward being able to pull in all the products and get a product level search across this environment. So I just wanted to sort of tie off with this last slide as a vision forward. Much of what we focused on is really the capture of data. I think we see that there's a real opportunity for us to move beyond just capture distribution of data, to think about how our data, both from PDS, from international archives, come together with tools and capabilities of the community. And I know Ross gave a talk, which I appreciate, on the spatial data infrastructure. We see that coming together. And I think it's good for this group to think about sort of a 10-year plan and where we could go. And there's a number of technologies which I think are ripe to be able to bring in to really approaches. I know there's some talks around that, but just to kind of tee up the fact that I think we're at a good juncture to think about how we can capture archives to provide more accessible ways to bring in advanced computing capabilities, really exploit and extract out data from our archives. And so, finish off, we've got 8 versions of PS4 that have been released. So it's highly stable now. We've got PS4 being implemented, a growing set of international missions, good progress towards international interoperability to realize this platform. And I think increasing opportunities really enable data-driven approaches. So if you see your table, there is some flyers for a workshop we're going to hold next year on informatics and data analytics. Take a look at that, sign up, tell us you're interested, and we'll be glad to bring you guys into that. And I think that'll be just a deeper dive in this topic. So.
We have just a minute or two for questions, David.
The mic is not hot. Up there it is. Okay.
Hi, Chase, Concepts. If support continues flat for the PDS, do you think it long-term can continue to support the archive and use functions simultaneously?
I think we have to figure out how to do a good balance of that. I don't think we can cut one without the other. So what we'll have to do is look at how do we sort of baseline our budget in a way that we can provide a core set of services. And if there's additional funds, then you really sort of build towards that future vision in a more diligent way. But I think we need to continue to provide it from NASA. Of course, they're going to provide that support, the core capabilities of support for capturing the data and providing user services support.
ETA on Federation-wide search API, which you know I've been
there is an initial pilot out that's REST-based, and you'll add more and more, but it ties us down. The search service is actually published, and there are some groups that are exploiting our search API. Good questions.
Yep, all set. Our next speaker is Steve Hughes, speaking on the PDS4 information model.
So I'm Steve Hughes, and I'll do the presentation on the PDS for information model. You've heard from Dan's introduction, and there'll be a lot of stage. So really, this presentation is just simply kind of a high-level overview, and just a slight more detail in terms of what the information model is all about. The information model was developed using 20 years worth of market, and we also use best practices for information model development. We didn't want to reinvent them, like we did back in 1990. So we decided to go out and identify some existing standards, mainly ISO standards. Information systems reference model. The idea of concept of what is a digital object, representation information object, what's an information package. They're built into the model. It's not always obvious, so that's what's making everything work. A lot of things that Dan talked about earlier. We also use the ISO IEC 1179. Again, a big standard that's out there. The schema, and use that for our data dictionary, and we'll talk a little bit more about the data dictionary in a little bit. For XML base, so we use the W3C standards, XML schema, and schematron. Drives the PDS4 information infrastructure, as Dan mentioned earlier, by providing the representations of the concepts or objects. There's things that have of interest in the archive. The relationships. Relationships, again, are key. A lot about relationships. PDS4 is all about relationships. And operation. It provides a shareable, stable, and organized structure of information requirements. System requirements. System development, you have a set of requirements for that system. Come out the information model are just as valid as are. And then finally, formal definitions that are suitable for configuring and generating code. Some things will come later. That is, this information model contains some information that the software is going to use. And, copy or manually copy information from the information model into the software. We're going to provide software JSON files, for example, in JSON format that will allow you to have access to everything that's in the information model. Many views of the information model. Here are just three. Anybody's worked with PDS for a while, especially PDS3, will probably recognize this view up here. Where PDS consists of data sets and time series, data collections, and the like. When we started PDS, UML and RDFL for developers to be able to access the information. And of course, this is the moment the updated the namespace registry is also bugged. Dan mentioned changes are getting fewer and fewer to the common model. The common model is the basis to everything. That's fine. The other changes in the operational area relates to the NSSC, the deep archive, by the way, and the final copy goes to NSSC for long-term preservation of documents. What this shows is that the information model, as Dan and I both mentioning, is becoming more stable over time. In 2017, so far there's only been 10 changes to it. And like I pointed out last time, change to more. Talk a little bit more about data dictionary governance. Most of the work initially was on developing that common model. There wasn't an issue about, it wasn't a big issue about governance, except of course, as Dan mentioned, we need to have the CCD change. Discipline models and mission models, extensions. Dictionary governance concept is becoming critical. Who controls what? And it's really very simple. Very beginning. There's a concept called the registration authority. Is the entity that has the authority to more and more dictionaries. Or it would be like NASA PDS or PSA, like your science archive. Basically, an institution that controls the registration authority then assigns stewards. The steward is an entity consisting of a group of domain experts that's given authority and responsibility to govern, and that means to create and manage one or more dictionaries within a domain area. So when you think of geometry, come together, geometry steward, and manage that dictionary as is together. One member of the group is identified as the primary steward, and the stewards in general can create the thing. And of course, that's what most of you see when you're looking at a dictionary. You're seeing namespaces, container, or logical grouping, single classes and attributes. So that's basically dictionary governance. The registration authority, which most of you would be under PDS, either PDS or PSA, for example. And then the stewards, which are assigned, which are actually people doing the work. Here's another view of that. You can see the common model, PDS. You can see the discipline level dictionaries we currently have. Imaging, geometry, and cartography. That are coming online by Maven, inside NOREX. There's a registration authority and a steward, and those govern those individuals. Okay, this is an eye chart, but this I think gives you a sense of where we are at this moment. When people ask, what's the information model? It's the information model at this point in time. Well, the information model was this green line. That's the common model there. Steward is PDS. This level is common. Yes, the steward is a PDS engineering node, but CCD. But what's happened over the last few years is we're now getting geometry, and we're getting cartography. Various dictionaries are coming out. This is a discipline level here. This is against the common model. Of course, the mission level coming on by the inside MGS. Basically is the information model. These are all connected in various ways, primarily that they're all consistent against the common model. To be able to show so some of the lines, you see the common, you see the registration authority is a NASA PDS, the steward PDS, the steward and the engineering node PDS, namespace ID is PDS, and the namespace, of course, that. Again, the registration authority. Geo is the steward, the geo node is the main steward, governance entity in the stewardship, and then the two namespaces. All this is in what we call the issues, what I just showed you in the previous slide. So the next release of the information model will be basically 29th, 2017. This was released to the public, and you can start the integration test for the system. That's 6 weeks before is the deadline for all SRs to be identified, to be implemented. There's 2 weeks then of implementation and initial testing. Integration, testing, preparation weeks, all paperwork done before we do the release. For anybody who wants to get something in, the design working group meeting for review of the SCRs is August 3rd, so give you a timeline in terms of. In summary, the PDS information model and standards are being used successfully, internationally being adopted by the International Planetary Data Alliance. Mostly work still to be done. People are still developing dictionaries, mission dictionaries. And what a lot of the talk will be some talk today on leveraging the information model in the system development and configuration of search engines and other services, development of software. Actually, one of the original points I made is that we built the model based upon the OIS ISO standard instruments to be able to audit and whether or not you're meeting the requirements of the about 109 of those requirements. Assessment of the PDS4 against the instrument called ISO 16363 and 106, and we found that the PDS4 10% of the metrics. And this was a breakdown in terms of basically three major categories: governance and organizational viability, the digital object management, how well you're handling your images and such. Risk, and we met that 80% of the governance, 95% of the digital object management, 6% of the infrastructure and security risk management. And the interesting side of the story is the PDS is probably the only PDS4 is probably the only reference implementation that currently exists of the OIS reference model. So it is becoming a knowledge. Any questions? Questions, go ahead.
I see. So you mentioned the the data dictionaries were still in progress. Do you have an estimate of whether all of the ones that might be needed have been started? Roughly, where are we in the development of the ones that are being worked on now?
Yeah, that's a very good question. Yeah. And anybody wish to correct me as I speak, that's fine, because yeah, a common model, and of course, the idea is that it's the discipline experts that decide what discipline you develop. If you're talking about the geometry dictionary and the cartography dictionary, those are the two major ones out there that are being used. I do know that the geometry dictionary, and Beth can correct me on this if I need to, I understand we have working pretty well, and we're still working on, is that correct?
No, there is a later and an older version. It's group based.
And that's basically the imaging node, and I believe that's in pretty good shape. I know that's not being used. I don't know of any gaping holes in it. The model as a work in progress at all times. I would say that like the common model of cartography is getting pretty close to that. Those have expert.
Comment on the cartography. Yeah, that dictionary is, as you said, I think we're using it. As it's getting used, maybe missing projections that we need to ingest into the primary projections and all are that we're mostly aware of are in use in the dictionary or defined in the dictionary. There's going to be additional special projections or special cases that we still need to implement, but we're all ready.
And one of my points is just that dictionaries finished. 10 years from now, they may be all finished, but I think fundamentally they are a work in progress in the sense that each new mission iterations and as we go along, but still not quite done with all of them. I don't know personally within PDS, I don't know of any missing. I guess we may come up to that. Anyway.
It's a very good point, and I think that's something that needs to be stressed over and over again, is that the PDS for information model was defined to be extensible. What we needed to do now, what needs to be done. For the first two out of the gate, I should mention that each of the nodes is allowed to define their own Rings dictionary for their particular types of metadata. Is one that's out for imaging. I believe it's being updated as we speak. Oh, of course, pretty wrong.
And around at PDS4, realizing the benefits.
This one is a clicker or just? Actually, sorry, I need reading glasses. So while I'm getting set up, let me introduce myself. My name is Ann Rao. I've been working for the Small Bodies Node at the University of Maryland for 25 years now, and I've been deeply involved in the development of the PDS4 standards. So currently the steward for the Spectral Dictionary, which is in active development. So this is the talk for the people who have been sitting there for 20 minutes thinking, why do I care? Or how does this affect me personally in my relationship with the PDS? So I'd like to hit just 3 of the major points. We had a lot of goals when we went and undertook the complete ground-up redesign of the PDS standard system, and I want to touch on 3 of the biggest ones where we're seeing benefits immediately as soon as we started to use the new standards. So you just heard about the details of the information model from Steve. So 3 of the issues that I'm going to cover. First is metadata control. In PDS3, we had both too much and not enough. Everything was all in one data dictionary, effectively in one namespace until the very end. And so if a mission wanted to add a keyword or modify the meaning of a keyword, pretty much the entire PDS organization had to agree. And that introduced a tremendous amount of inertia and an awful lot of arguing, and it wasted time. So we wanted to get rid of that. Every keyword was pretty much defined as a standalone concept. Very few actual structures were defined in bio purposes to define data object structures. So keywords had no context, additional meaning, or nuance. That our archive was organized around physical distribution. So we talked about volumes, and that meant that some of the information that you might want to find was hard to find. In point of fact, it was almost impossible to find a document in the old volume system unless you already knew where it was, because the labels didn't contain enough information to make them locatable in a search engine. Finally, every time a new person came in and had to learn how to write a PDS label, they would have a list of concepts they wanted to express, and they had to go paging through the data dictionary trying to find the keywords that would address those concepts. So there was nothing to tell them, this is what should be in a label, this is how you should describe an image. The best they could do was take an example that was given to them as being pretty good. The labels got better as time went on, but consistency, ordering, organization was pretty much however each mission wanted to do it. And so each label provider, individual system, and looking from label to label, even for the same type of data, could be very confusing because you wouldn't see the same things. So the benefits that we get from these, first of all, we managed, I think, to pretty much eliminate keyword arguments. Product has become the new granule. The physical proximity location algorithm is gone, and we have a very high degree of predictability in our label organization now, which is useful on the input end and on the output end. So looking at these in more detail, arguments. So as you've heard, the information model is divided into namespaces, and we have disciplined namespaces to tell everyone how to display images, for example, so that always looks the same and is always in the same location. Cartographic information, geometric information, everyone uses the same keywords, they come in the same order, they have the same wrapper. So it's very predictable. You can find it programmatically by knowing the entry point. Everybody finds it the same way. When you get down to a complex data set where the missions want to track mission metadata, search for large data sets from large missions, and can help large missions correlate data between instruments and spacecraft for spacecraft. They need to be able to define things very specifically. We can delegate authority to a mission steward and let them develop their own mission dictionary using precisely the same tools that the discipline dictionary preparers and the core dictionary preparers use, as you saw in the LDD tool. Examples how to do it. We can review the definitions that they provide in their data dictionaries so that we know that their documentation for their own metadata is as complete as the documentation for the metadata in the core namespace. And we train them how to do it, and we leave it up to them. The tools, and it's syntactically valid, it's okay with us, reviewers, but that's the level of control that we have. So we've, I hope, eliminated arguments about what can go in their namespace. For particularly complex missions, we can subdivide the namespace. And the fact that we have this model-driven methodology that gives us the namespace partition means that we can make sure that something that a mission wants to define does not actually affect the definition of any of the discipline dictionaries or any other mission. So we can partition, have what I like to refer to as rigidly defined areas of doubt and uncertainty, which once again gives you that predictability. Product is our new granule, and everything in PDS4 is a product. It has the same basic structure. In fact, I have a poster on that, which is down of this hallway, that shows you the basic outline for an observational product, but in fact, higher level aggregate products and high level have the same sort of structure. The things that are labels, the unique identification, the modification history, citation information, if this is something that might be referenced in the literature, these are all defined in the core. They are all a single label. When we have a collection, what you might think of as a data set of related products that you want to group together, we have an aggregate product called a collection. A collection is just a product that contains a data object that defines relationships between other products. And so the collection is itself a product as far as the system is concerned, and it is searched at exactly every other product. Similarly for documents, the metadata for documents now is completely independent of where they came from, so they can be searched across the board. And, even the next higher level aggregate, the bundle, which is a collection of collections, is once again a product. It defines relationships among collections and provides history and provenance information for the entire product. And since everything has its own unique identifier, everything can directly cross-reference anything else it needs to cross-reference. So if you have an image product that's a calibrated image and you want to directly reference the raw image and the calibration information that went into it, you can do that, which means we can set up search and packaging services that can get you of the product as well as the final product and deliver it to you as one package, and can offer you the calibration document that describes how to use the various bits and pieces and put them together. And finally, predictability. Because of the model-driven design, we have a very firm basis. And Steve likes to think of things as growing downward from the model. I like to think of things as being built on top of the foundation. But the effect is the same, it doesn't change. That contains the critical identification information, descriptions, so that everybody is describing data in precisely the same way. And it also contains the language of definition that is used to define other namespaces. So in the core namespace, you will find things like unit definitions, so that if you have a metadata that has units associated with it, wavelength, speed, things like that, there is a standard way to define that in all dictionaries so that you can program to that. So the language of definition is in the core, and then that means you can use that language as you're developing your own dictionary and to build on what's there. And when we need to add additional metadata to the core, once again, we use the same tools and it builds onto that stable base. So you have the predictability of the baseline, the minimal information. You know exactly where to find it. You know exactly what it's going to be called. And if you go digging into the details of the information model, you know exactly what's required and what is optional. For a programmer, you have all the predictability that you need to actually write general purpose software to read any image in the entire PDS4 holdings. We never really could successfully do. We could do it for large sections in PDS3. In the past, the assumptions would have to move in and they would break down. And that's basically all I have to say about that. So I will take questions. And if not, I will put up a shameless plug for my posters. So there's the
Again, a couple minutes for questions. Any questions?
I don't have a question, as a comment that Ann is participating and is one of the instructors in the PDS4 training on tomorrow. And it's available on Thursday morning as well, if and when questions come up after the training tomorrow. So, thanks, Andy.
Speaker will be Steve Joy, speaking of strategy of writing a good data management plan for a ROSA proposal.
All right. So I wrote this talk partly because associated with the PPI node are constantly being inundated with requests for letters of support day before proposals are due. And to me, that indicates people are not taking the time to really think through their data archiving process. The other thing I've done is I've set in various review panels for proposals, and I have seen some very obvious examples of people that did not take the time to write a good. Well, NASA's really taking this seriously these days. You're going to get a much better likelihood of being selected if you write a good data management proposal. So one thing that you want to do is make sure that if you're going to be archiving with the PDS, you contact the node early for your letter of support. PPI is that with products that wouldn't naturally belong with us, they belong at small bodies, they belong at atmospheres node. So it gives us time to redirect them to the right location. So if you don't have enough time, that doesn't happen. And we also find that the data management plans just don't they don't demonstrate any kind of experience with the archiving process. Have any experience with remote?
Use the arrow key.
So an overview at the top. In general about archiving plans, and then I'm going to, at the end, talk specifically about archiving with the PDS. The key thing is to start early. You need to select the right archive. The right archive is not always the PDS for the types of data that are coming in. You need to contact the selected archive well in advance of the proposal deadline. You need to learn the nomenclature and the standard practices associated with the archive, work plan and budget, PDS archiving. Start early. This is the key element. There's nothing you can do that'll be more helpful to your process than starting early, no matter who you're archiving with. Because it gives you time to research where the right archive is. Organizations have different requirements. PDS has its requirements, but it may turn out that your data belong with HITRAN, or they belong with some other organization. They may be heliospheric data primarily, in which case they belong with NSSDC. They have different standards. So it forces you to think through and understand the standards that you have. Be secondary benefits from starting early and thinking about what the end products are. Very frequently, if you think about what you're producing, you have to kind of back up to the steps that it takes to produce those sorts of products, and that may areas or pitfalls that you might avoid along the way. Selecting the right archive. You have to archive with the PDS or an equivalent archive, and that PDS, you typically have to demonstrate that it's not an equivalent archive. The PDS archives data from the planets, comets, asteroids, small bodies, dust, etc. If you curate samples, we will take data, which is analysis of samples. The archiving within PDS, as everyone should know by now, is organized by sub-discipline. The proper organizations for archiving heliospheric data is NSSDC-A. Software models, any kind of software, there's a lot of software archiving now being done through PDART, done through the NASA GitHub. Not archive executable software. It will archive algorithms and documentation, but it does not software. Analysis samples have multiple potential archives. There may be some cases where those data do belong in the PDS. I've seen examples in some of the different nodes. Up to you to figure out where that kind of data should be archived. It may not be the PDS. Say if you think PDS at some particular node, go to that node. Look to see if you can find anything similar. Maybe because there, others probably wouldn't look there to find it. Nomenclature and the standard practices of the archive. Over the last 45 minutes or so, PDS has transformed from the PDS-3 standard, which used terms like and catalog and using using terms like bundles and collections and products. You need to use the right nomenclature. Archive should be defined or described using the SPACE standard. It has its own nomenclature elements like services and data can be broken down into numerical and display and other forms of data, rather than products. So using the right nomenclature is helpful. Archiving code, you should have knowledge of coding, creation management. You develop along feature branches. You do build roll-ups. Your NASA requires that you use GitHub. About documentation through Git commit and using the Git for notification to your user base of releases and for an issue tracking. And all of those things are built in, and you just say I'm going to dump a bunch of code in NASA GitHub, that sounds like a wasted set of dollars because nobody's ever going to be able to make use of that. Practices demonstrate knowledge of them in your proposal. People planning on creating landfill analysis that are not going to be archived with PDS should understand requirements for that archive. I know HITRAN in particular has very specific formatting that they require of their data, and you should learn that and demonstrate an understanding of that in your proposal. Include a realistic work plan and budget. Most common errors that I find when I'm looking at these things is timeline. One of the things I'll see frequently in data analysis proposals is somebody's going to propose to do recalibrate some data, use that newly calibrated data to develop a model, the results, and the newly calibrated data come out in year 1, year 3. That's the wrong timeline. If you're going to produce the product in year 1, archive it in year 1. So try to keep those things. And then not enough time to produce and validate the archive. There's an awful lot of stuff where people work all the way up to the end and have only a month or 2 at the end for generating the entire archive. Things are more complicated than that, and you need to have enough time. Money allocated to the task, that's just, you got to allocate the funds for it. And the wrong personnel assigned to the task. Frequently is all of the archiving is assigned to a low-cost student worker. Don't necessarily have all of the insight and understanding to really do a good job on the archiving. So you should show some effort from senior scientists in the archive design, in the documentation review, and in the data validation. You don't want to generate a whole bunch of data been validated by a senior scientist in the archive. Enough about the generic stuff, in particular when I talk about archiving with the PDS, most of the data coming out of Rose's proposals will end up with the PDS. Must comply with the new PDS-4 standards. There are some missions that are still archiving PDS-3, and you might be associated with them. Grandfathered in, that doesn't apply to you. If you're applying under Rose's, you're committing to PDS-4 standards. Certainly, it's exceptionally important for working with PDS. And of the node, again, as I've mentioned before, is very important up front. The node early enough in the process, some of them may give you some initial thoughts on the initial design of the archive, and the amount of time it might take to generate and validate the products. And you're going to archive with the PDS, please let the node know when you've been selected so they can begin folding to their already full schedules. I'm not going to talk about this much because you've heard this in talk after talk this morning. Or as products organized into collections, organized into bundles. Be useful for people who hadn't had 45 minutes of this. documents, there are several documents that are out there available for proposal writers. There's the concept, PDS4 concept document, tag or the individual proposer's guide. These are both very good documents. NASA has an FAQ on data management plans, and they're also providing a template this year for data management plans. There are also tools, if you're selected, to help generate. There's some at AI, there's some at small bodies node. I know there's some at atmospheres node, but I couldn't find one online. I went looking for them, but I know that they're there. There are also tools to help with creation and validation of archives. Are available out there for the group. Both all bodies have this available there. You get to actually writing your data management plan, you should start out with an archive overview. This will typically consist of saying that you're going to produce a single bundle or data collections, depending on exactly. You have one or at least one document collection. You may or may not have browse collections, etc. Management plan that discusses what you're going to produce in terms of this nomenclature will demonstrate some understanding of the PDS process. The archive needs to be discussed. Here, the total expected size in terms of volume, megabytes, gigabytes, terabytes. These are precise estimates. These are scaling estimates. Whether you're talking about 1 megabyte or 40 terabytes, it's important for us. The number of data file structures that you're going to use. Every file structure that you're going to have is going to have a different label template, time to produce, and time to validate. Total number of each type. Every sort of one-off file you're going to have, you can hand generate a label. But if it's a multi-file product, it's going to require a pipeline to produce that file type and that label type. And so again, that goes into the timeline and cost estimations of this product. The general timeline that I've laid out, and notice it has no time axis. It's just sort of these are kind of the steps that you follow in the order you typically what you're going to produce. Products. That's with the node to make sure that on the right that what you're producing F5 and PDS doesn't accept it, that kind of thing. That you iterate there with the node, you create and templates, you verify that those labels are valid before you make thousands of files according to a template. You write your documentation that can overlap a lot of this. Writing the documentation. Then you generate the products and labels, you assemble and submit the archive to PDS. Peer review, and there's time for lien resolution. So after the review, you're going to get comments back. You have to have time scheduled for that. You think that the liens are resolved, you're going to submit data. That shouldn't be an end of funding, because you may submit something that you think has resolved all the issues, gets back to PDS. Things. Team members' roles and responsibilities. Everybody that's in final archive should be data management plan, designed by senior scientists, implemented by staff programmers or postdocs, and executed by junior staff. Senior scientists shouldn't be involved. Even if it's just for a short amount of time to review things. So a small senior scientist involvement in the demonstrates a commitment to the archive process to the reviewers. Works in the archive and its narrative. one quick bit of some changes to things in 2017. Programs do have this data management template pulled out sections. This should look very familiar because these are the same topics I've just been discussing. The couple of things I want to point out are the intended repositories and public access, and the plan for enabling long-term preservation. These for you. PDS keeps all the data online, provides access to users for no charge, and that's long-term preservation. You can expect them to be preserved for at least 50 years. That PDS maintains multiple copies. Data only in formats that can be fully described in its required metadata. There are no proprietary or transitory formats allowed. In software, you could say that PDS does not archive tools, but does accept algorithms and source code as forms of documentation. Summarize. Select the right archive. It's not always PDS, regardless of who it is, and that context that can be helpful when figuring out how much effort budget you should have in your proposal. Standard practices of the archive. Technology is very different. Include a realistic work plan and budget, and leave schedule margin for unexpected delays, hurdles, PDS coordination. PDS coordination, the nodes are busy. And just because you're ready to submit something doesn't mean they have time. They may be in the middle of a major mission and have to wait 3 or 4 before they can get to your thing. So leave some margin in there. And if selected, please let the node know so that they can begin integrating your effort into their time, into their timeline.
We don't have any time for questions right now, but we're going to have a break just after this next speaker, so please find ideas right after that. Sorry. So our next speaker is Kate Crombie, systems engineering approach to planetary data archive development.
Hi, my name is Kate Crombie, and I'm going to give the second part of Steve's talk. And we did not crib off each other's talk, so this may look kind of familiar with what Steve was talking about. I'm going to expand quite a bit on the start early. Okay, I'm going to talk about a systems engineering approach to archive development. Data returned from our NASA planetary missions. That's the scientific legacy of these endeavors. It is our national treasure. So, group, I don't have to tell you how important keeping the data around for the future generations is. NASA requires archive raw and calibrated data products. Through AOs, they do encourage the archiving of derived data products. A lot of different ways to go about getting to these archives. On programs, I've worked on mission programs. A systems engineering approach is really helpful because it looks at the archive as an integral part of the complete mission system. It's not some afterthought at the end that, oh my goodness, we have 2 weeks and we've got to archive this data, let's do something. As a life cycle, from development through proposal, all the way to the end, and into the mission planning and operation, and it ensures that the archive is developed in coordination with your mission. 5 talks in, you're going to see a requirement here soon. It's coordinated with mission requirements, mission operations objectives, and it is an integral part of the ground data system processing. One of the first things to do if you want to start early from a mission perspective is to appoint a mission archive scientist and would be responsible for the overall planning and development of the archive, an interface between the instrument teams, especially on missions these days. Missions are getting more and more complicated. Different instruments are trying to take coordinated observations. So if you have someone at a higher project level who has insight into what each of the individual instruments is doing, you can make sure that you're keeping your coordinated metadata so that the team, as well as the people who use the data afterwards, can actually make the links between the different data products. Interface between the ground system and the instrument teams, and they will be the person who has communication and starts that dialogue with the PDS node that they will be delivering the data to. Scientists can inform and enforce the mission-wide metadata standards, as I just said, or, thanks Ross, the spatial data infrastructure that is necessary to be able to coordinate those different data products. Somebody at a mission level who is looking across at the entire archive and the entire system, there's risks for the mission because it has a very unique view of what's going on in the mission. They're looking at the final data products that are going to be produced, but to get to those final data products, you have to go through the entire mission system and identify holes early. So they can really be used as that risk reduction. So the first thing you're going to want to do when you start early, and this can be in your proposal phase, this would be step 1. It might be a phase A study. It can be adapted toward a DAP program or a ROSES program, so where you are. But first thing that happens is you have requirements development. You get a mission concept. What are we going to do? These level 1 and level 2 science requirements are addressed to address the objectives of the mission. Level 2 science requirements talk about the data that needs to be collected to make a data product that is going to help address that scientific. That level 2 satisfying data product derived products. They're made up of the lower level data products, so the instrument observations that your mission is taking. Ability matrix to map how these level 2 products get their input products, which are the lowest level products that you're doing, and trace that back to high level mission requirements. So you can then use this traceability matrix to develop your data management plan. So here we are, the requirement So a level 2 science requirement might be something like producing a topographic, particular spatial and vertical resolution. So your level 2 mission requirement is a model. Terrain model, you need maybe the mass of the object, the gravity of the object, and some spice terms. Products. Pipeline, calibration, validation pipeline from the LiDAR. These are the instrument products. You might have radio science, and then you might have a spice processing environment. So you need 3 different processing environments to get products to go into your final derived product. You might also have different working groups on your team that are producing these individual products. What you're doing is you're identifying the links from your high-level derived, lower-level data products. These lower-level data products, the things that you're going to archive. You're going to archive this as well, but you certainly need these. The other thing you're doing is you're identifying links to your mission observation plan. These observations, you certainly can't produce that product. So again, you have some linkages that you can look at to make sure your observation plan and your data products align. You're also identifying interfaces between software processing environments and mission working groups. So you're getting your software, your observations, and your data products all in line here. You can then use that traceability matrix to start developing your data management plan. And this could be your proposal data management plan. But a data management plan is not only useful in your proposal stage, it can be a living document that carries through the whole of mission development from proposal all the way through archive delivery. This is the thing that's going to have the top level description of the mission data processing elements and responsibilities, the relationships of all these groups and all the products to one another. It will include data processing required to produce the product, level 2 science requirements. So this is how kind of everything fits together. The relationship between the mission, and here's where I'm before early and regular communication and the PDS. Important to archive development. Your PDS node, they've done this before, kind of a few times. Really help you guide and narrow your focus on didn't think you needed to be looking at. So and early communication is key. Part of the relationship with your PDS node is that you're going to have to develop development schedules, peer review schedules, and delivery schedules. So they can also help you and knowing what they have to do and what their schedules are. Your mission is going to fall in line with all the other activities that are going on. That's something to really note. Okay, so you put your data management plan together. You have a grand plan of all the things that you want in your archive. What are you going to do next? The next stage is your archive development. The data products that you in your data management plan, initial product definition by all your product formats, and develop your prototype products. Develop your draft archive documentation. Then the prototype products and go into what I've been calling an initial review. This is kind of where you can put your whole archive plan with prototype products in front of your PDS node and get some feedback. This is not to products. This is to make sure that your archive is complete and that you don't have any holes in it. We're planning to develop for the archive. Really useful, and they are within the PDS4 standard, especially as we're from PDS3 to PDS4 and the earlier missions in 4 standard. I work on the OSIRIS-REx mission. It was really important for us to get some early feedback on the products we were planning and the formats we were planning to use to make sure that they were going to be PDS4. It's really helpful to get that feedback. You can also identify any holes that you might have in your whole process at this early stage. Expect that you're going to have updates based on your review, and you might have to iterate a few times through this in order to get everything perfectly aligned. which are a big set of steps, is your design and delivery. So once you have your prototype products, you might want to set up an automated pipeline to produce products that you're going to be producing over and over again. These would be your instrument, raw through calibrated products. You processing them, so you want to put an automated pipeline in place to be able to create those products. When you do this automated pipeline processing, PDS node, you'll want to put together a configuration management plan so that if you need to make changes here, you have a good way of delivering changes and documenting your changes. Peer review, a lean resolution. Go through this process a few times. You're getting close to your delivery test, that you're ready to go for when you have your nominal data collection operation. Finally, when you've produced your archive, it will go through a delivery review and then be made public. Steps and work really hard with your PDS node. Review should be more of a validation of these data products, and this should be fairly rapid to get to a much more rapid turnaround in your being made public. In summary, a systems engineering approach sees the archive as an integral part of the whole mission system. It is not something to be left till the end again. Requirements inform your archive design, and your archive design needs to be relatable back to your mission science requirements. Review results in a comprehensive and scientifically useful archive. And communication between the mission is essential for a successful archive.
All right. I'm sure that our speakers will be around here for questions, but we'll go ahead and have our break and resume at 10:15.
Mine was a question. Yeah. Yeah, well, so, I mean, and so it got accepted. Yes, it has to. To east of that. Yeah, that's a. What I know is that was negotiated to be east of that.
Yeah.
I was looking at you yesterday, I'm like, wait. I couldn't see your back legs, I was like, wait a minute. See, I was with the four kids. And around. Yes, actually, through Facebook. So, and I keep asking, what did you do temporarily. I think we should start this. Yeah. So we're going to get restarted if you want to find a seat. So our first talk of this session will be Ray Arvidsson talking about the PDS Orbital Data Explorer.
Thanks, Dan. So going back to Kate Crombie's presentation about the need for end-to-end or systems planning all the way from concept for an archive and working with the instrument or providers, getting the structures in place, the types of products, the documentation, going through a validation, a peer review, getting things into the system, ingested, and out to the community. For the geosciences node, which handles data from the inner planets and Earth's moon, is talked about our approach, which is on the right-hand end, after a lot of work getting the data into the system, and working with many, many missions and instrument teams, and right now, working with 36 investigators from PDART and DAF proposals that were successful. On the how does the community get to the data? And you can look for the data by browsing, but also there are two capabilities that we offer that are HTML based. One is the Orbital Data Explorer, and the other is the Analyst Notebook. Orbital Data Explorer is for dealing with orbital missions, and the landed version, the Analyst Notebooks, Tom Stein will talk about coming up in this session. But I want to focus on ODE. Planetary data system, this is just some of the basics, and you've heard some of this morning. We work a lot with missions. It takes a lot of time working with individual instrument teams to make sure they understand what's required of them contractually, ethically, to get the data out to the community. We do peer reviews. We really try to ensure that the data are preserved in formats that are long-lived, like PDS for the community. And there are a set of discipline nodes that we've talked about before. Page for the PDS Geosciences node. And the focus again is on Mercury, Venus, Earth, Moons, and Mars. Extensive cooperation with other nodes and holdings. And the ODE, in fact, reaches out and subnodes, data nodes, data in order to allow the user, you guys, to have one-stop shopping to find what you need, download. So the focus of ODE is going out and getting data that we either have house or all these nodes, our data nodes, to go into our processing system with a front end that allows form-based searches and also map-based searches, so you can browse what you think you need, put into a cart and download, or go and individually download what you need. And you'll get a message by email saying it's ready, an FTP site where you can go and get it, download it, and do with it within your analysis environment. These are the data that we have currently in the system. This is a well-used system, folks. In May, I just had Dan Schultz kind of tabulate the use. We had 3,650 individual users who downloaded 1.6 terabytes worth of data. So it's up and running and used a lot by the community on a worldwide basis. This is the front page for ODE, and there's one for Mars. There's one for all the lunar data, one for Mercury. Venus. Venus is dominated by the Magellan data, as you might expect. You can do form-based searches, map-based searches, by IAU, defined feature types and names, and come up with the data that fall within that area. Do searches by Mars Reconnaissance Orbiter coordinated searches, in that when a CRISM observation is requested, it should come with a CTX, a context image, and also a high-rise image. It's kept by us and put through the system so you can actually do coordinated searches to find the 3 groups of data sets. That's how the mission was designed. Systems. REST is an acronym for a long set of words that basically says, if you don't like our interface, you can get into our database from the side and build your own interface. That's the REST. And we can customize deliveries for archives for deliveries. So search for products, that's the next page on the upper left that you get. And you can define the instrument and the product type that you'd like to search for. By product ID with keywords if you don't remember the whole thing. Or feature, by time, by observation angles. You can do it on a map-based capability or a form-based on the bottom. Showing one of the CRISM products that you can take a look at and browse. And we don't have high-rise data, we don't have CTX data, we don't have themis data, we don't have but we go out to those nodes for visual display and pulling those data back in to put into kind of a bundle for you to download by FTP. This is a result once you've done, for example, a product search for those products, and those stars are wildcards, but if you don't remember the whole thing, you can wildcard it. And those are the observations that come back in terms of viewing by a table, so for Mars. And then you click any one of those up and you get a browse image together with other information that you can pull up. If you like that, you can download it directly. But when you go to the download page, it gives you all the other goodies that are usually associated with that data product type. And those of you who have broken into the system, ancillary files that you need. The download page, and again, you can structure the archive that you want to put together in a particular way and the type of compression, saying it's ready, and we'll go to our FTP site and get it down. Base search in which the footprints are there, and you can interactively look at the files of interest, and they light up on the map page in order to help you select what you need. You have underlays. So for example, this is a messenger-based search that we're looking at is a messenger color-coded surface relief map, and then we have those data sets overlaid, and that's the box of interest that you've selected. And once you do the view selections, you can go through and highlight as you go through those particular data sets that will show up on the left. They'll pop up on the right, so you can kind of get a feeling for what you want. And then you can check those you wish to put into a cart for downloading. And there's another example with other data from Messenger, and on the left, what we're doing is looking at the products that will show up on the right, so you can kind of interactively figure out what you need. Boxes, update a cart, so in the end, when you're ready to download, those are all there, and they get kind of put together in a zipped archive or a tar or whatever you need. Also have a granular data search, so those instruments that collect data as a set of points along track, custom set of points within a given area or given time range, and have those downloaded as an ASCII table, shapefiles, images. For everything, but for example, the laser altimeter or device data sets, it certainly works. If you're really interested in the combination of high-rise CTX and PRISM at the same time, we have those keys in there that allow you to do that, and we're looking at the 3 data sets there. And then here's one for Magellan, the long track radiometry data and topography data acquired by the small antenna looking down. together with the F maps that were put together here in Flagstaff. Yes, and we're looking for combination with the light blue areas, footprints, and then you just about see all the along track observations. So you can kind of customize, get those all together, and they'll come down for you. The REST interface, you really have to be an aficionado of getting into databases by yourself. But that's available, and there are about a half a dozen sites that actually get into our holdings off to the side base through the REST capability. We do this for you guys. So we really like feedback to make sure we're doing with the data that we have what's required in terms of having you get to the data sets in an efficient way so you get what you need, get out of there so you're not spending a lot of time trying to figure out how to use it. So you can go into your own analysis environment to do the work. That's the Orbital Data Explorer, and in a few talks, Tom Stein will be talking about how we handle the landed missions in something called the Analyst Notebook. So I'd be happy to answer questions. Oh, come on. Do I have to pull some of you up? Questions? No.
You got more to say, Rick?
Oh, good. Tim's up. Yeah, what do you want, Tim?
I'll ask you a question. How does this compare to some of the other search tools like Pilot, more of the GIS tools like JMORS? So this over one of the others.
This is a good question. This is a search and retrieval capability, not an analysis capability. This is, I want these data sets, so I want to get into them. I think based on use and download, it's the most popular one. It's not a JMORS. JMORS is more of an analysis tool. Hey, what do you guys have? How do I get them? How do I efficiently find them? How do I get them downloaded so I can import them into my analysis tool? If you go to the EOS DIS, the Earth Observing System Data and Information System, do you know how many interfaces there are? And they're all different. I use any of them. So I make one of our graduate students do it, and it take like a day or two. So if you think ODE is hard to use, let us know, so we can make it more efficient for you guys. You guys are paying for this as citizens. Make sure we're compliant with what you need. Remember, we only have data that we can get from the missions and from providers, derived products. Now keep pushing on NASA and projects to get more derived products into the PDS, because right now that's the Achilles heel.
All right, thanks, Ray.
Okay, so our next speaker is Rob French, who will be talking about OPUS. So continuing the theme of tools, access, and get into the data.
All right, good morning, everybody. For those of you who know Mitch Gordon, you may be wondering why I look different than I used to. I'm both shorter and more clean shaven than I used to be. Mitch was unable to make it to the workshop this week, so he asked me to give his talk for him. Since he made the title for this talk himself, I wanted to just point out one little special feature here. Figure out what is special about our talk title compared to every other talk title at this workshop. The longest talk title. And actually, if you use the modern SI unit for market speak, which is the tweet, only talk title that actually requires 2 tweets in order to put the top title down. So anyway, I'm here today to talk to you about OPUS, the Outer Planets Unified Search Tool, and I'm one of the co-Is on the project. Okay, so OPUS is a feature of the website that used to be the PDS Rings node. And in fact, the website is still-rings.seti.org. The recent funding extension that we did earlier this year, we renamed the node to the Ring Moon Systems node. More than just rings. We do everything having to do with the outer planets, their satellites, and their rings. So we thought this would make people a little less afraid to come to the site if they wanted to look for other types of data. It is to be your first stop for all of the information related to the outer ringed planets: Jupiter, Saturn, Uranus, Neptune, and not ringed, unfortunately, Pluto. We have a little bit of information about Venus, Earth, and Mars that are derived from the flybys of Cassini and Voyager, but that is not our primary focus. We have information from these various, I'm not going to name them all out, but Cassini, New Horizons, Galileo, both Voyagers, and most recently, we started adding Hubble solar system data. People may not realize that we are actually retrieving solar system observations from MAST. We're incorporating it into our website and into our search system, so that when you search for solar system objects, you can get data products that are from all the spacecraft in one set of search results. Data we don't have, for example, dust data, we don't have plasma data, we don't have radar data, that kind of thing. So got to go to other PDS sites for those. But for imaging and for spectrographic data, we want to be the primary site that you want to come to. Tools, we would also like to be your primary site for that as well. We have a variety of tools that are available on the website. We have planet viewers, which allow you to look at, give information about what your viewing point is, for example, Cassini at a particular date and time, where the camera was looking. It will give you a nice plot of the planet, which rings you're looking at, which satellites were in view, as if you were actually seeing it from the point of view of Cassini. You do the same thing with Voyager stations, things like that. We have moon trackers that give you the east-west plots for the various satellites for the outer planets. We have ephemeris generators that generate these tables for you for information about all of the icy satellites of the outer planets. And finally, we have a set of dedicated tools for each of the missions. So you can see running off the bottom of the screen here, we have Cassini tools, the New Horizons tools. And these are ones that are specifically designed not only for analyzing the data that has come back from these missions, but also for helping to plan those missions in the first place. We're holding perhaps on that one. Finally, we want to be your first stop for information related to these planets. So most recently, we have put a lot of information on here to support the ROSES grant applications. So for all of the various DART proposals, as well as for SSW, we have dedicated pages which give you the information that you need to include in your proposal, not only for how to sort or how to archive the data afterwards. The user's guides for the various instruments. We have information on the planets themselves and details on all the various spacecraft instruments. Specialized example where you can do complete archive in all the various spacecraft. We have the calibrated images that we have done ourselves for both Cassini and for Voyager. We have occultation profiles from Cassini and Voyager, and thumbnail images. So here are the 4 instruments that we support on Cassini. On the left, that's an ISS image of Saturn. It was taken through a red filter, and so the thumbnail image that we give to you is red, so that you don't have to look at the name of the filter, you just look at the thumbnail. That is a Sears set of observations. This is the infrared spectrometer, and this shows the path of the Sears focal plane as it went through how the observation happened. Next to that is a UVIS spectral observation, and on the right is a set of DIMS cubes. Use those instruments, those actually might mean something to you, the thumbnails, and see what information you're getting. Finally, which is the main subject of this talk, we have enhanced geometric metadata. So we have the ability to search on things like latitude and longitude, lighting geometry. If you saw my talk yesterday on Cassini navigation, all of the different backplanes that I was talking about are things that will eventually be put into this as things that you can search on. The backplanes that I talked about yesterday, but we do not have the re-navigated. But you're only off by a few pixels. It doesn't change your searching very much. We have just added in the very last week geometric metadata for Uranus and Neptune. So for the rest of the talk, I want to walk you through one particular usage case for this. And in particular, I would like to find images across all spacecraft that show you Mimas. So the Herschel crater is at latitude on the equator, latitude 0, it's about longitude 100, plus or minus a bit because it's a really large crater. And so to run Opus, what you do is you go to the main PDS Ring Moon Systems website, and this pops up an environment in which you can set various constraints on your search. Is that there are 1,342,000 and change different data products that we have available if you don't put any constraints on it. Without more constraints that I really don't recommend. But the thing that we would like to do is look at memes. So without giving any information about the particular planet or particular spacecraft, I essentially want to go over here to this surface geometry. Geometry tab, choose what particular target you're interested in. We're going to open that up, and it's going to pop up a little box here that lets us select all of the different targets that we know about. Saturn, so you can see the different Saturn targets. Satellites, including the irregular ones, including Saturn itself and Saturn's rings, are available for you to choose. This is a green number that tells you that if you were to select that particular constraint, results you would have left to you. For our particular purpose, we're going to choose Mimas. Mimas, there are two things that happen. The first one is that you see that you get now 31,000 browse products, just like I said, the little green number. And the second one is that you get a new menu over on the left-hand side, surface geometry. Here about latitude and longitude. So I'm going to pop open the planetographic latitude, select the observed planetographic latitude, and it's going to pop up a new set of constraints over on the right-hand side. Range that you can reasonably select. In this case, since we have images of Mimas that go all the way around the moon, it says we can go from like basically -90 to +90, which makes sense. We only care about things around the equator, so we're going to select things that are within plus or minus 10 degrees of the equator. And you see that the number of browser results instantly drops down to 5,789. Okay. Now we care about longitude, so we're going to go over here to longitude, select the longitude. Things that are vaguely around the 100 degrees, that shows 80 to 100, just sort of arbitrarily. And we did that, we now have 4,618 browser results. So this is all very fast. This all happens in a matter of seconds if you type it in. The database searches. Finally, we only want things that are high resolution. So I want to go down here to the resolution item, select the finest observed resolution available, and say we only want things that are between, let's say, 0 kilometers per pixel and 4 kilometers per pixel. You can see the range that's available here is from like 0.2 for really serious up-close images, all the way up to, well, before I had selected it, all the way up to 29,000 kilometers per pixel for very distant images. And that drops us down to a much more reasonable 508 images. So now if you click on the Browse tab at the top, where it says Browse Results, all of the different images that you selected so far. Notice that they're colored by the filter that was used, like we discussed earlier. And you may notice that the two in the top left-hand corner look different than the other ones. That's true. If you simply click on the one in the top left-hand corner, you get a little sidebar that pops up, and it gives you some metadata about that image. That is the Voyager 1 image. It was taken in 1980. It tells you the phase angle, what moon it is, and this data that shows up on the side is all configurable. From all the different metadata available, you can choose which image shows up in this sidebar. Two over to the right that actually looks a little bit more modern. You can see it's a Cassini image that was taken in 2005. Now all of the different spacecraft results are all merged together in one set of results from the database. More about this particular image, you can go down here to the view detail. It pops up a page that has all of the metadata available to you on one page. And there's a lot of data available. I certainly can't scroll. You can see how small the scroll bar is up there in the corner. That shows you how far you can scroll down and still get reasonable data. So you can get the general constraints. If you scroll down a lot, you can get all the things related to Mimas. And then I want to do one last thing here, which is I want to show you how to download the data. So to get a more reasonable amount of data and then add some more constraints, I'm going to say, well, I only want the Cassini ISS. I want a clear filter. I want only from the narrow angle camera. And I want things that are between 1 and 4 kilometers per pixel, so I don't get the really up close ones. There are only 11 browser results left when I choose all that. And then if I go over to the selections, sorry, if I go back to the thumbnails, oh, and there's one last thing that was kind of cool, which is I asked for the phase angle at the body center to be around 90 degrees. So I want the terminator to actually be right in the center of the image. Images that all cut, right, with the terminator right through the middle. You can see how you get these nice relief on the Herschel crater with the shadows. So I can select all of these thumbnails, the selections page, and it gives me the option of what kinds of things I would like to download. and I can click on download zip archive. It builds a zip file for me in real time, gives me the link, and lets me download it. Like not on your personal computer for your use. You can choose raw images, calibrated images, thumbnails for HST things. For Voyager, you can get calibration. There's all sorts of different things you can choose depending on the types of images that you select. I'm going to leave you with some information about developers. We do have an API, like everybody else does these days. So you don't have to use the website. You can write your own software that does these queries and downloads the data. Hub archive that allows you to do, has a lot of software on it for doing things like reading bigger files, for parsing PDS labels, computing gravity fields. We have our own Python implementation of T-Spice, which I don't recommend you use because Andrew's much better now. But anyway, that's all for you to use publicly.
Sorry, on your list of targets, there's you got the inner planets as well.
So the only thing we have for the inner planets, if you actually were to select Mars, you would find out that we had it's because Cassini flew by Mars, right? Or Voyager flew by Mars to get gravity assist and took a couple shots. I mean, we have Earth on there too, by Earth, but it is not. We don't collect any of the the actual Mars mission data. And it's unified search, and it really is outer planets that have gone to outer planets.
All right, so our next speaker I'll introduce is Tom Stein, who will be talking about the PDS Analyst Notebook for MSL in MER.
Good morning, everyone. I'm Stein with the PDS Geosciences Node in St. Louis, and wanted to take time today to talk about our Analyst Notebook web interface on the notebook for the MSL and MER missions. There are also notebooks for other landed missions like Phoenix and the Apollo missions on MSL and MER. Is the Analyst Notebook. As it says here, it's a tool to support landed mission science. Integrated access to these peer-reviewed data, released data that are provided by the instrument teams, and all supported by the documentation that describes the data format, calibration. And one of the strengths of the notebook is to give insight into why and how particular observations were made. So for MER and MSL, there are public and team versions of the notebook. The public version is updated with every public data release. For MER, that's every 3 months. For MSL, roughly every 4 months. So 3 or 4 times per year. And is updated or two as the new data and documents come in. And the purpose of that team version is to help us with data validation, but importantly, built on this strong collaboration that we have between the data providers and PDS. And that collaboration and relationship starts with mission selection. Data management archive plans are written. Communication lines get open to benefit both sides of the data production and archiving. So on the left side of the screen here, I've listed the elements that are typical of a standard PDS release. MER and MSL right now, those missions are archived in a PDF3 format. Archive data, the EDR and RDR products, such as the software interface specification, so valuable to understanding the data format and instrument works and how the data are acquired. Also calibration of data and reports. Standard release of PBS archive, but then there are additional data and tools that are provided by the notebooks. Products that come along, some of them produced by the science team during the mission, where the instrument team might say, we didn't think we were going to archive, but we'd like to get those out there. We also have some extra documentation, including these daily reports that come members of the team, and the mission manager and documentarian reports that come in part of the archive and not archived anywhere into the notebook to help build that. Was this decision made? It's asked. And along with that, historical reports, some other resources, and we'll take a look at these as we go through here. And then finally, the last column, these with a lot of tools for searching through the data, in the traverse of the rover on a high-rise base map, and zooming around, panning in, and associate with a geographic location that I'll talk about. Tools for some data analysis and even some data gain easier access to the data. We'll talk about all these through some screenshots. So if you go into the notebook, which is the URL here, if everybody does it right now, you probably won't get it. But the first thing you notice is that there's an opportunity for creating an account. That's not required. You can push this button that's kind of outlined in orange here, kind of anonymous access. Encourage users to create an account is things style of using the notebook. Your history is captured for your use, kind of a list of documents and things that you've read. So as you come back in or from another device and log in, you've got access to those items right away. This is the very beginning of the notebook after you sign in. So we, on the left side, have a series of tabs, like the tabs of a notebook for the different sections. We have a control area in this big gray space, a working space for viewing data products and documents and such. Changes that we've made recently is to make the notebook a web application. So, or you might have found the occasion where you were looking at some, you went to go do a search, the map went away and everything you were looking at got lost. But now the web application just stays there and everything stays open as you go through the different sections. This is an example of clicking on the red target tab there, and I opened up both a table, and for MSL there's this the MSL targets. Those are the targets that are, they're not IAU named, but they're the ones that the teams are using for doing the operations. And one of the great things about mission summary table is that for every sol, there's just a real brief description of what was going on and a quick overview downloaded as a PDF or Excel spreadsheet for sleepless nights where you really want to memories of the first 1,000 or 2,000 sols. The sol summary tab, this orange one here, is going on. First off, there is a gray summary block. Sorry, I'm not very good at this laser. It'll be a whole lot of things. So every time a sol shows up in that block, it's telling me what was the Earth date, the little mission solve summary for that day about what was going on. How many data products were collected. The little colored squares you see there are one per instrument. When they're shaded in, that tells me data were collected that day, such as the first AP there is APXS and so forth. Whether or not there are documents and activity plans and targets and such. So this is a timeline view of the activity plan for that solve. And what we've done is actually match up these data products and back on the other. So clicking on these red outline is their time worth solved. You can get direct access to the data. Another view here into another solve summary, and you see there are a couple of solves that are listed here, with the second one being expanded out to show targets. Each of these sections can be expanded, but the target one is further expanded to show that solve. Kind of in the background is a and then popped open this particular target rock, and then went in and from up here images of this target. So as you see here, there are 300 other images from which you can view this target. And even though the target was defined on Sol 796, there's some solve, so you get an opportunity to view a target from the approach angle, perhaps in the rover has gone off somewhere else. You can think about the context of that target. Here's a search screen. Searching for data. There are opportunities here to search data documents by free text. That's type in that whale rock target name and find perhaps documentarian or mission manager reports that. And on the right side is here's another image that's open. Every time I'm opening something I'm looking at, this is a until stop here somewhere. Bob in here. Making official science quality and use-worthy. They will be excited in there. In the meantime, we've used auto-stitching software to make these context mosaics so we can understanding of the broader context for individual images. So other screens are, here's a traverse map for another entry point into the data by the rover traverse. Here is a user tab showing my history, my documents I've had open, and targets. And a quick click on any of those brings that object right back up for another time. It is looking at an image that's part of a stereo pair for a HASCAM profiles, make measurements on there, and then you can even draw annotations if we want these to get saved. The next time you come in, you open up the image. It's still there. That's part of the bonus of using an account. These data, the measurement data, out as a spreadsheet. Another view. So in the resources, there's some other things that don't quite immediately fit into the kind of search thing. So here's a context mosaic, and you can also see there are references down here to patients and so forth. For MERV, there are data sets. One of them being, as an example, of finding APXS oxide abundance data. Going into the resources and data sets that are listed here, you can get a link straight into the whole collection of data or just the individual data sets. The notebook or different approaches to find things. The solve summaries we looked earlier, you saw there and APXS data for a particular data. You're looking at this presentation for that particular APXS observation. Here's a link. Hey, are you looking for the oxide abundance data, which are not single products that just show developments here that we're going adding into Notebook and appreciate feedback from our users. Most of the tools and enhancements we put in are because users have requested it. So thank you very much for your time. Stunned. Usually. All right, great.
All right, so this is Jordan Adams talking about the NASA PDS imaging and the ability to access for imaging data.
All right. You guys hear me? Good? So I think this is the last search. Yeah, the best for last, I guess. All right, there we are. I'm the system engineer for the PDS. I was here on, but I wanted to do something a little different. They want to just present all of our tools again. You can, or go to the last text, so you can find all the information. The goal that we have for PDS, imaging node, and all of PDS really, is to provide easy access in our archives. So for the imaging node, I don't know how many data on our local machines, access to data on other areas and things like that. So we want to make it as easy as possible for people to access this, not only through our user interfaces, but also through software. To automatically pull in data, access data, or integrate with other search tools so that you don't have to download all of our data in order to actually be able to access it. It doesn't make any sense, right? Talk about user interfaces, the pretty things, right? Well, it's kind of pretty, I guess. So the Image Atlas, which is developed by Alice Tamboli and Kevin Grimes. I'm just here presenting for them because I made an abstract. And so basically, I'm just going to talk to you about some of the upgrades that we made. Again, you can just know how to use it. Hopefully, it's intuitive. So some of the things that we've improved upon since we're improved Google-like search, so you can do things pretty easily through easy searching. Image content search. This is some pretty cool stuff that KiruUX that we'll be talking about later, which I'll walk through also. Using convolutional neural networks to actually without actually having to know that there's something in this image, right? So you can actually figure it out using the pixels and the information in the image itself. We have some better faceting. The back, if you press back, it actually goes back in your search. It doesn't just remove your search altogether, which is nice. And then new data. So we have New Horizons. The messenger data is not in there right now, sorry. But the New Horizons data is in there, and so you can see Pluto and all that. Here's the website. You can actually Google it too. It actually should work, hopefully. If you Google that, it should come up with our website. Here's what it looks like. And then, so the fun HTML here. So data search. So I want to kind of show you how the data search works, which should, again, be pretty straightforward, but or if you've used it before, you might think it wouldn't work right. Say you want to see Cassini ISS image. It's just a coincidence. I know this is a big Cassini day, apparently. But so you type in Cassini. Look at that. Oh my gosh, it actually says something like that you expect. Oh my It does the same thing too. That's great. If you press enter for both of those, that you hopefully want that are expected. If not, that was a bad search. That's not, I can't change what you're looking for. So one of the other new things is this image content search, which again, Kiri will be talking about later, but I'll just kind of jump through how it looks from here. Click open that guy. You'll see this drop down. It's not going to be this big, but it will be on the sidebar. And you can see the different kinds of image content that we have available. The naming we're still working on, so if you have some ideas of what these should actually be named, please let me know. We are always looking for better feedback for that. So as an example, if you click body full, look at that. They're actually full bodies. It's pretty cool. So this is a pretty simple one, but there's some other ones that are neat too. Wait. Let me see a slide here. Okay, well, actually, there's a lot more of these. So if you actually scroll down here, there's some for MSL, Galileo, and we're improving that. And we're trying to turn it into actually, we're working with Christine and MPSS at JPL to kind of come up with a more generic structure so we can actually implement this across many missions, not just for specific ones that scientists will pay us to do. So this is a little bit, we're trying to build it up a little bit more, and if you have any ideas, we're always looking to make this better. Okay. So search protocol. So this is from, if you go to this website, it should take you somewhere that I created yesterday. That was the API for how to access our data or our index for our search programmatically. So this won't be pretty. If you don't care about that, you definitely don't want to go here. It will be JSON. It's really ugly. You won't want to see it. But from a software developer, it's great. So if you go there, I'll kind of give you an example of how this might work. So say you want to look for curiosity mosaics, things that Bob does and his team, from planet day number 1500. For this, you can actually go to this, and it won't do anything, but you could go there. And if you add some of these parameters, you say spacecraft equals curiosity, you say spacecraft equals curiosity on product type as mosaic. Number is not, that's not the right planet day number. I have to change that. It's because they have prettier images, so I changed it. So if we go there, this is what's going to come up. You can pull out some metadata. This is from our database, and so we're growing this every day. But basically, there's some improved metadata. So especially for things like Cassini, there's data that's not just in the labels, but things like these image content type classifiers. So it gives you this added information, which I think is really useful beyond just the label data. Label data is obviously very, very important, don't get me wrong. But they improve data over time, and so we can add that in here into our index that our search is based on. Yeah, and so here's one of these pretty images, right? There's better ones, but I didn't, I should have asked you about them, sorry. And then so the other way to access this, or our data, is webification. Now this is a little bit different than the other way. It's still JSON, so it comes back, it's nice, it's cute. But the difference between this one is that this is more like traverse, an easy way to traverse this. And I'm going to steal some stuff from Chase Million here because he also, we presented this not too long ago, I think last data workshop, and he has a nice little program that we're going to use. But basically, say you want to traverse and process Cassini ISS image data. Cassini, again, this base URL. You can display the contents of the directory, which, if you look here, obviously the left side looks prettier, but the right side is much more easy to read from software. And then if you go, so if you go to the next one, you can say, okay, I want to get the image metadata like this. So this will basically take that label and make it look like something much more machine readable. And then you can output it as a picture, so it looks nice. Access this to actually get the raster data. And so this is, again, this is a Python program that I borrowed from Chase. Thank you for that. And it basically will take this data and process it, and then you can. So this This is kind of really nice. I mean, again, if you're not a software developer, this might be like way over your head. You don't care about this. That's great. And go to that. The beginning of these slides are much nicer. The idea behind this, again, is to be able to integrate all of these tools, right? So Chase mentioned earlier this ability for PDS to have this API protocol that can actually be used across the nodes. And this is absolutely something that we're interested in. And so I'm trying to take a step forward towards that. And this is just that right now our API is very much rudimentary. It's kind of like throw spaghetti at the wall, see what users actually are searching for. And that's we're using our search engine metrics as well to kind of figure this out. And there's also a way in the API to do, you just have a specific label keyword you're interested in. You can just do PDS dot something and search for it. The API also isn't up and running right at the moment, but it will be. Promise, next week, hopefully. And also we're gonna have, if you go to the website for imaging node, or the imaging search, working on a little bit of a UI facelift also, that we are weekly on, apparently. So that's it. I flew through that. Questions? Please, a lot, because I didn't even repeat yet. Good. Oh, okay.
You know your classification for the image content?
Yes.
Is that,
I have to turn it off and on again. Hi. So the classifications for your image content, was that done manually or is that automated?
The service that we have now is automated, but it took a long time to seed the convolutional neural network, and Curio will get into all the fun details about that. But yeah, that's we're trying to build it out into more of a service, and actually, hopefully in the future, make it more crowdsourced. So we can basically say, to help improve the network, is that if you say, that actually is not a crater, I don't know why you think there's a crater in there, you can say it's not a crater and help us build it over time. Yeah, so yeah, if you have any other questions, comments, concerns, if they're more, like if you want to complain about something, email is the best way to get hold of me. If you're actually calling with something more interesting, you can call me. So. Okay. All right, thanks.
The messages.
Since we have a little time, I just want to comment that the virtual box that is in use for the PDS4 training tomorrow, so don't all download it at once, but I'm now putting it today on a different network, and so I will have it on the thumb drive an hour or so. So if you need it and you can't retrieve it yourself at the meeting here today, some people will be able to get it to their hotel network later on and so on, but we'll bring it on some thumb drives. The idea is for you to download it and install it. It starts tomorrow, so be aware that it's 3.5 gigabytes, which I did not mention earlier. Okay, so you have it as well. Okay, so Ed already has it.
I think Sean's got one too. So.
7 or 8 minutes to transfer it.
Thank you.
Good old.
No, but I mean, the point is, there's only 15 minutes allowed for
Yeah,
solution.
on a front end, right? Yeah.
Yeah.
That's a lot. The next talk is Lynn Nicholas talking about ELSA, which is a tool for archiving drive data with the PDS atmosphere node.
Did everybody hear me all right? Good. So we're going to switch gears a little bit here and go back to PDS4 and some tools that are coming up that the talk following me will be on creating labels for PDS4 products. So this is the work that we've been working on at the Atmospheres node in New Mexico State. So let's see if this. Good. Okay, to start with, now the PDS4 we were talking about it this morning was is a new requirement for all data analysis programs, And the big thing is that few of us have any experience working with it at this point. We're starting to get that user base building up now. So the big thing here is we're moving away from this ODL label metadata management and going into an XML system process to some new data providers coming in. And so what we've decided to take a kind of a different step back and look at this approach as an opportunity to educate on what the PDS4 system is really all about. And then so we're developing this tool to aid with that transition to PDS4 for our data providers mainly, but also other data providers as we to learn PDS4 while building their archive products with us for submission to PDS. So this is, again, a revision, review of what we've had all morning, but there's a couple things I want to. Bundles, collections, products. We've heard this all week, all morning. You're going to hear more of it in the next couple days. So the idea is everything is a product. All products have these XML labels. If it has an XML label, it can be registered in the system. It can be found here. The key to that entire thing, the glue that makes the whole system work, are these logical identifiers. Logical identifiers. We call those LIDs, logical identifiers. They are done in this URN format. Source name here. And there's an example of this down here. And the idea is that the first part of this is the resolver. These guys are responsible for finding it. But then your bundles, these are done in a logical fashion. So you have an identifier for the bundle, identifier for which collection you're talking about within that bundle, and then the product IDs here. Important part that I'm going to come back to as to why we're focusing on that. But the big thing, again, as we heard earlier this morning, all labels have the same organized layout, which is really good for moving forward. So I want to get behind the philosophy behind what we're doing at Atmospheres to start with. So a couple things here. Steve Joy had a good point on this earlier about the archiving process. And in addition to his start early, is hugely important. I can't say that long enough, loud enough, everything else. The discipline note. So this starts at the beginning. So when you have the proposal process, as you know, the DMP process, data management plans, you have to have this communication. And it helps with the scheduling all the way through. It helps with you getting the things that you need early on so that if any problems do occur while you're doing this, you have plenty of time to fix it under your schedule. So this communication continues all the way through to the review process and going through to the final validation certification of data. After the communication, the thing I want to say is that the product design labels, as you heard from, I think, Kate and several others this morning, this is an iterative process. We start with some base product templates, maybe go through and make sure that we're getting all the metadata that makes sense for your data products and making sure that that's captured in some good way. And then what we like to see is, during this iterative process and the communication part of this, is to see some sample products to spot check. I don't want you to do an entire archive, and find out, oh, there was some systematic errors we could have taken care of early. Spot check where you send us, here's the product and it's a corresponding label. Let's check it out and make sure everything is where it should be before we do the whole set of them. To the bundle for the review. So we want the whole thing here, and this is including documentation. Documentation is hugely important, especially moving forward with everything. We want to have some way of describing how the data were created, how they can be used, what are the assumptions behind everything we have. The peer review process, lien resolution, which you've seen a little bit of this earlier, so I don't want to spend too much time on this. Which those liens get resolved, get into final validation and certification. So we're doing this from a data provider motivation, and these are a couple of things, several things that have come up as for things that we've noticed while we've been working with our DAP programs that have been coming in now, that are the first generation of these PDS4 ones are starting to come in now. And so the big thing is most providers have little or no experience submitting to PDS in general. Things that they've never done PS3 or PS4, so they have very little experience with the PDS. number of projects submitting data to Atmos. So again, another thing with maybe they just have one project they want to do. They want to have to spend all this time learning all of this information about the PDS and get done. With PDS4, few of us have experience working with XML files. So that's a new hurdle. Providers that archive data may underestimate the time needed. This goes back to the things that Steve Joy was talking about earlier about making sure that you understand the process as you go through it and the time that's involved in each of those steps, and not to shortchange the review period and the lean resolution to make sure everything's good. We're looking for a quick and clean solution, providing maximum output with minimal effort. The big idea. So what that leads us to is looking at our provider feedback and the experiences we're gaining from talking with the providers as we're doing this process. We're looking to move towards doing most of our labeling for these types of derived data products coming in, small projects. Usually, we want to base this largely on templates. So we have some experience doing PDS4 at the Atmospheres node. We want to be able to use that experience in the most efficient way, and that you guys can get in and use the system, use these templates and produce labels in a fast, efficient way and get the most effort out of this. Do tailoring of templates within the node, can provide more detailed metadata and better labels. This is, again, that iterative process of making sure that we're getting all the metadata we need for these things. And of course, the more complex the product is, the more complex the labels will be, so we need to look at that. The most common issue is knowing how to fill in all the interconnected fields. So as we heard through the information model and all this morning, PS4 really interconnects everything. So these lids that we were talking about at URN, and all the relationships that you build up with these products and how they relate to the collections and how those collections relate to the bundles, and information from missions and instruments and all that stuff. That's one of the things that we need to have our data providers. And so what we're using is using all this feedback experience to create a tool that helps provide access to the PDS4 system and how it works, so the education part of this, and then looking at providing a line of communication from support from the node. We're enter ELSA here. We're calling it the Education Label System for Atmospheres. What we're doing is designing a multi-purpose and tool environment for Atmos to use the burden of archiving for our data providers. Here, as to learn more about PS4, we want to build bundles and using label templates, submit these to the Atmos, and that queues them up to be able to do the lean the review period, managing of the lean resolutions, and then basically getting these things staged and out for final release. This is a screenshot of what we've got so far of the system here set up. There. And with 4 basic tools that we're looking at using, and these are in various stages of development right now. So this is why Steve couldn't find our site earlier. We're working on it. So I'll go through each of these tool systems and give you a little breakdown of what they're doing and what we're hoping they're going to do in the future. The tool is basically right now it contains links to documents and other resources across PDS for learning about PDS4. Many of the PDS4 resources are based on our work with LADI missions, Maven mission, migration work that we've been doing internal with Node. But we're also, and then anything that we've been doing within NELS projects as we go, we're adding to this. Eventually, once the build a bundle tool, which I'll talk about next, is up and running, we're going to basically use that as a demonstration to be able to walk you through the whole process and have a tutorial in this particular section to go through that, but that's not quite ready yet. Build a bundle. What we're trying to do is provide a tool to set up all your templates so that you can basically grab everything you need, get the bundle and collections set up, and then move on to doing product stuff. So the idea here is that this is going to build your URNs, your lids, to the template. So that product, you don't want to mess those lids up because that's your interconnected glue, right? Get those as regular as possible. So we provide a way to populate these into the label templates, and then you can take those templates and do what you need to do for the rest of the metadata. So right now it does all the internal ones. So browser, it goes from the in your browser. You can do it for your collection products right now. And what we're adding is a way to browse context files. This is the type of thing like the catalog files in PDS. So this gives you mission information, instrument information, target information. Those are in the catalog at engineering node, and we're working on a way to for easy selection of those. We can actually auto-populate the other stuff right now, and I can show demos of this in the next 2 days while we're here during the yeah. So this is we're working on. I think Dan mentioned about the new security requirements that are going down. Atmospheres has been hit by this as well, so we're in the process of instituting some new systems like a password protection system. Set up as the free account system, and then you'll have a workspace that you can save stuff as basic on this. And we're eventually going to be adding to product label templates here that we can. Atmospheres node is based on table data. We have some image data as well, but most of it's tabular data. So we can do templates for working with those. And we're going to have a basic system to edit like headers and all that information, put those in so it'll automatically generate that as well. It's in PHP and JavaScript, but we've been investigating moving to Django because all of our in-house stuff are done with our students, are usually done with Python routines. So we want to have a way to group that together. And it's here to be integrated with the submission tool. The submission tool is not up yet. Right now, this is a secure FTP thing that we just SFTP in and drop stuff in a file right now. We want to be able to link this together so that you can, once you do some pipelining with the label templates we just made, move into a holding area at Atmospheres. And then we can go through and stage this for the review process once everything's complete. Basically, this isn't up yet because we're waiting on the password security stuff for setup accounts. The peer review is partly up and running. What we have here is a short web form. A lot of the review systems, especially for derived data products, are really short. Science reviews want to come in and they want to get stuff together. A lot of times our reviewers are like, what am I supposed to review? So what we've done is done a guided system with some questions and web forms. You can fill it out. When you're done with it, it converts it to PDF and sends you a copy, sends me a copy of the review. And so there's some integration here that can still be done to make that process more efficient. So current status, I've kind of gone through some of this. Right now, we're doing this in conjunction with our PDART 14 projects that are coming in within this next year. So I'm using that experience to tailor this. I'm doing a lot of what this ELSA tool is doing manually to test the procedure. We get feedback from that. We're coding it up and making it automatic online. So it gives us some confidence that what we're doing is going to be useful. In the year, we're hoping to have some select open beta testing. So there's some projects that are coming in that make more sense to use this right now in our early stages. So we'll funnel people to that. And so, like I said earlier, bundle collection, label creation, auto-generated populate the lids, context product selection right now. And we're beginning to look at some other query-driven editing of basic templates to be able to speed this up for everybody else. Here's some conclusions. And I think we've gone through most of this already. We're trying to ease the burden and aid in the education for PDS4 and increase in communication. So if you're planning on doing this, contact us. See me sometime this week. I can give you further contact information. I'll be at the training session tomorrow as well. So.
Oh, you got it.
All right, so our next speaker is Sterling, who will be talking about PDS Label Assistant for Interactive Design of Flat. Okay.
Great. All right. Hello, everybody. My name is Sterling Alderson. I'm here to talk about PDS Label Assistant for Interactive Design, or PLAD, that we designed to simplify PDS4 label template building. We're specifically interested in the actual templates themselves. That's your product observationals, your document labels, that kind of thing. Oh, let's see if this works. Yeah, I'm good. Okay, so why PLAD? We've found that building PDS4 templates requires knowledge of XML and PDS4 data dictionaries, both of which are not trivial to learn. We're finding that we're working with a lot of people that have, say, no XML experience or coding experience. And even though XML is technically not coding, it does require somewhat of a technical background. The PDS4 rules and dictionaries are evolving very quickly. PDS4 data providers can book 126 pages, and it seems like about every 6 months, a new version comes out, so that is constantly changing. And a lot of missions just don't have the funding or time to learn all of this. And so we want to make the actual template building as easy as possible to use the interface. So missions have limited time, and so we had a previous tool that was called a label design tool. Found working with users directly that it was too complicated. We important it was to make a tool that was as simple and easy as possible to build a PDS4 label template. So we took our lessons learned from that, and we came up with what PLAD is today. And we made a web-based wizard, so it's a step-by-step tool. So you log in, it's all on the web. You say, I would like to make a new label. You select what dictionary you want to use, and then you are presented with what kind of label you want to build, and then you go through each section of the label and just fill out what parts should go in there. We provide inline documentation that we get directly from the PDS and Steve Hughes' data model. And we also limit users so that they cannot add, say, too many elements that would make an invalid label, or remove elements that are required by the PDS4 standards. For, say, an attribute that has a list of enumerated values, we provide that information in a dropdown. So you minimize time going to the manual, the search, all that. It's all provided inline. We're also trying to capture best practices too. So there are some things that, say, the PDS4 model requires, but there are some things that aren't specifically required, but you should include anyways in your PDS4 label. So we're trying to basically gather as much information as we can into this tool and make it. So this is the interface. It's relatively simple. On the left, let's see if I can put these over here. Anyways, the left-hand side is the part of the label you're currently working on. So we go through each section of the PDS4 label. You have what you can actually add or remove at that step. You can provide sample values. So you're really building a template here, right? This is something you would hand off to the software engineer and say, hey, it arrives from our spacecraft. We need to use this and populate this XML document. But if you wanted to, say, include example values, you could do that in this tool, and it would appear in your output label. Maybe that's for reference or for review. You want to show the PDS kind of what you're thinking will be captured in that section of the label. So at the end of the process, after you've gone through all the steps, you get your XML document. You can then save it. After each step, it's automatically saved to the web-based tool, so you can come back here and go back to the previous step. Perhaps you want to tweak something you had, added or changed earlier. Your review process, and there's some sort of change that needs to be made, well, you can do it very quickly from this tool. And what's really great is that you didn't need to memorize all the PDS4 rules and standards. As long as you tool, you will have a valid template. Now, we're not currently validating the values you put in there. That's something that you can do later with the XML schemas and schematron, but we're looking into that and a bunch of other features actually. So that is available for use. You can access it at plaid.jpl.nasa.gov and make an account. It's obviously free. We were able to open source all the source code for this a couple months ago, actually, and we're continuing to, on a somewhat regular cycle, push our internal GitHub repository to the public to contribute code or provide suggestions or integrate in your own tool or use our API. We're certainly interested in collaborating and making, the best PDS4 tool possible for at least the metadata templates. So here's just a high-level view of how the tool works. Basically, we ingest Steve Hughes' data dictionaries, which are giant JSON dumps of the PDS4 model, and then we process those to dynamically build each step in the tool on the fly based on what's provided in the PDS. So really, whatever the PDS does or changes, we ingest automatically, and so we can or a new requirement or a new, really anything related to the model, we automatically. And that ensures that we're making valid labels when. So just some technical information. Here's the software we're using. It's all web-based on the front end, JavaScript and HTML with some JavaScript jQuery libraries. And obviously, Steve Hughes' model really drives the tool. And we have a database that keeps track of users and your saved labels. And then we have some IDE tools for developing the software, and we obviously are using Git and making this software available to everybody. Here are some things we're currently working on. We're looking into doing starter label templates. So let's say you really like how your camera on your mission to say Insights camera. So you'd like to start with Insights camera label and just tweak it slightly for your mission. Well, you'll be able to do that. So we're looking in ways of entire label and allowing you to tweak it as needed and perhaps provide sample values that are specific to your instrument. Also looking into starting a label from an Excel document for batch editing. We found with some more comfortable just filling out an Excel document. So in the interest of making this tool as easy as possible, we're looking into doing that. Also an effort to automatically fill out parts of the label based on your previous questions. So like you, for example, select version 1.8 of the PDS4 data dictionary, well, we can fill in some parts of the label based on that information. Or let's say you're an orbiter, well, we can fill in some information in the label based on that too. So just trying to the information we have and make it more useful. Access is provided in line, so we're looking at providing suggestions based on what we're already doing, but what PDS recommends. So that will shorten, say, your peer review time so that you can reduce the duration between you going back and forth with the PDS node and have to meets all these best practices. And mission attribute and class support. So let's do a mission dictionary, which we do allow you to build the tool. We're looking at actually building schemas and schematrons out of that. Right now, we just start on the label and send it to PDS or the PS node that's the one you're working with, and they can kind of work with you on that. But we're also looking at some of that information as well. Collaboration. So if I have a label in the tool and I want to share it with else that's working on my team who also has a Plaid account, well, maybe even collaborate so that they can edit it or tweak it or provide comments and that kind of thing, or even just access it, really. We're interested in feedback. Constantly trying to get feedback so that we can make this tool better. And so we'll be doing talks and demos today and tomorrow. And we'll be also looking at doing PDS3 to PDS4 label conversions where we actually build a PDS4 label based on a PDS3 label and use the generate tool to map elements between the two. So we'll be doing that later in the week. Or check out the tool now. And these are the contacts. Any questions?
Thanks, sir.
Yeah.
Just to clarify, did you say you can or cannot utilize a discipline dictionary?
Discipline dictionary is integrated. We also get those from the information model, so we get them. We don't have all of the data dictionaries supported, but we're working with the nodes to get them in the tool. We get some placeholders for a couple of nodes dictionaries, but and a couple are still in development. So as those evolve, we can integrate them into our tool.
Okay, so you would integrate them at that level. We wouldn't test them ourselves as a user.
No, we handle all that. There's no managing, say, schemas or schematrons or JSON dumps. That's all done on the server. And we provide this tool as something that people can install themselves on their own machines, and this is part of why we open source it. But we've found, this is one of the lessons learned we found, is it's best if we manage it. That way, existing versions or older versions on other machines or that kind of thing, and it's just easier that way. And that's really one of the benefits of software as a service, right? Is that you have a central management server. And so if you want to update the software, you just do it once. If you want to update the dictionaries, you just do it once. You know, distribute it to 100 people and then hope they can all install and upgrade, or manage them upgrading, that kind of thing.
Sounds good. And if you didn't use your template to develop a label, can you use Pilot to ingest someone has already developed a label and use it?
So this was actually kind of what I was referring to with the starter templates. You cannot currently ingest a label and have the tool built out yet, but that is something that we're looking into.
Is there any context sensitivity? If you tell it that you're building an image label, does it know to put in the geometry subsection?
The best practices thing I was referring to earlier, currently not yet, but we are building a system to tip, like if you select this item, we really should include these items in this dictionary and these items in that dictionary, just so that we, do more than just the minimum, actually follow the best practices.
Thank you.
Yeah.
In your XML template that you showed, that the export button,
yeah,
were fields that were empty. So were no tokens that are placeholders that could be replaced with actual values.
Right.
Is that an option, or it's something that you have to do as post-process?
So you could fill it out in the tool and have sample values in there, but really we're building a template, right? And this is something you would hand off to a software engineer to fill out.
Right.
So it's up to you.
But there are multiple ways of doing it. If you do it from your tool, you generate all that and you dump objects. Or if you do it by generate tool, then you have to have some tokens in the template that would be replaced. So I was just asking if there's this option.
Okay. Yeah, you could fill out the velocity template variables in the tool and use that as a mapping.
Thanks, Ron.
Just a reminder, we're collecting thumb drives up here, so if your thumb drives, grab lunch. Great. So our next speaker is Tan, who will be talking about China, the ongoing work of Science Data Archive and release in China Lunar Exploration Program.
Mr. Zhou cannot come join urgently, so I'd like to do the talking in place of him. Have any questions? Okay. We are from National Astronomical Manual Science about the exploration program and the data management and the mission. Okay. China Lunar Exploration Program, we also called China Program. It has 3 phases: the orbiting, the landing, and the sample returning. 5 will be this year to realize the sample returning. Timeline of the our research and Deep Space Center. Research and of the China program is have 3 segments. The headquarters located in Beijing, and we also have 2 ground stations. Our mining work, our mining work is the operation management, the data process, and the data management. And also, there are 2 new subsystems: is storage and the processes subsystem, and the sample and the data analysis subsystem. I will mainly talk about the data subsystem. Of the data management system is the data infrastructure management, more in the data management and data release. The voice of the data. I will talk about the ongoing work in DMS from the data archive and data release. Our data is classified into scientific data and engineering support data in journal. The scientific data includes the original scientific payload data and the results data from the analysis of the original data. Engineering including the management, communication, navigation, scientific design from the channel exploration process. According to the process degree, channel data was archived in different levels, and the level 1 and level 2 are archived as the PDF standard. Level 0 data is the binary data. All the channel data are naming roles. Example of the channel data name file. We can see that the mission information, the payload, the data type, and the orbit number are shown directly in the file. In level 1 and level 2 follow. However, there are some difference between the channel data and the PDS data, such as the catalog. Most of the PDS standard data object and the data label is separate. But in channel data, archived in data level C2B, and the channel data do not description files, so documents, and so on. And the channel data object and label in only one file for the data product in channel data. from channel 1 is the PDS version 3, and channel 5, channel 4 information will take PDS XML to describe the PDS physical and the data label will separate. So the data will take the PDS standard and still preserve the data label data characteristics. Example of the label of the panoramic camera of 3. And for the release and backup of the channel data, we developed SunUpUs. It is a CS software. It's for high data management operations such as upload, search, storage, engaging, and the BS website. Is public user could download channel data with the software. SR is the software used for data disaster recovery and data backup. The server of this software is in use. Products from channel are now available. Used to register and download the data on our website. Now, archive the total value of the information, and we also produced some as the high resolution global image. The resolution is and the high global DM, and so on. Our is the only one authorized space center, and DMS has data from the success mission, channel 1, channel 2, and will connect the channel 5, channel 4, and the Mars. And channel data has been used in several lunar science research and archived some interesting scientific lunar science. This is the website. We can search the data according to the payload data level. When you get the data, you can this data. And this is the WebGIS. The menu will be included the channel 5, channel 4, and the MOS. It will be launched in this year. The channel 5 rover will soft landing on the get the lunar samples and then rise to the channel 5 orbiter and send the lunar sample back to the Earth. Channel 4, channel 3, almost the same with channel 3 in engineering structure, but very big scientific objects. So, channel 4 is first on the lunar far side in human history, and firstly set and release satellite in Earth Moon level L2 point for the communication and provide data platform to the lunar far side research. So there were 4 international cooperation payloads installed on Channel 4 platform. And in 2020, we will launch the Mars probe and to realize the one stem of orbit, land, and petrol. Thank you very much. Thank you for listening.
So I have one question. Where where do you guys see yourselves in terms of looking towards PDS4 and PDS4 and so forth? So you know, much of this I think is probably based on PDS3. Still moving to PDS4. Yeah. So that may be something, you know, within PDA or International Planetary Data Alliance that you guys could consider. Thinking about your role in IPDA might be really helpful. Thank you. All right, well, thank you for your attention this morning. I think we are on lunch break, so I'll hand back to Lisa for logistics.
Very much, Dan and Lynn. I just wanted to remind everyone that we're trying to gather for a group photo this afternoon at the end of the sessions. The mappers end a little bit earlier, and it isn't clear whether they'll join us or not. But so if you're available and interested, we'll be out in the lobby there. And I'm hoping that we won't have so many people that we can't use the staircase. And that, after the lunch, come back at 1:30. Around 5 o'clock, yeah. This session is on schedule to end at 5 p.m. today, so roughly 5.
You have this afternoon tomorrow. Yeah. I'm mostly here just coordinating, talking to people that I don't get to see very often. This afternoon, if you want to sit and talk, and certainly Joe and I will be doing some demo it's all day long. So it can be, you can stop in at any time. I don't expect there's going to be a lot of fields of part of it. Yeah.
Quite interesting.
Yeah.
So the room will be locked again today, you did leave things in the room, the room will be locked?
Yeah, I was going to go there. I can't take those.
Well, I kind of asked. I think that would be
Just talking.
Yeah. I'll have to take a look at it because one of the things that he said, and so I was well, one of the, well, Sebastian got up to ask me a question. They cut him off because what the question he was going to ask is PSA. I think the answer is. I mean, if you look at the unless it's USA.
Oh,
Yes. Yeah, well, also, they're not ready. So, and you and I discussed this when you were putting the proposal. I always talk about
where is he? How come he's so? He's the one who talked to you today.
Yeah. So.
Emmanuel was
It's not good.
Yeah, they're moving, they're like, just getting rid of other. I want that.
Does he come to the office or is he just, okay. Yeah. Yeah, I'll see you next week.
That's right. It's the interview, right?
Yeah. Yeah, it's small bodies,
So I told my. Not only did we have a good day of interview. So anybody needs help with that, we can tell us, who's has some experience with that. I said,
you can play the beat for the extra word.
We're trying to.
So a reminder that we'll lock the room, and what that means is you can go out, but you can't come back in. So if you need your stuff over lunchtime, just take it with you. Or stay in the room, that's fine too. But you won't be able to get back in while it's locked.
Ah, hey, yes. So you do all the stuff. No, I can, you just tell what your name's on. Okay, all right. Yes. So does Ed tell you that we're related?
Yeah. You and I?
No, Ed and I are, Ed, right? Yeah, so his sister was married to my first husband. And I had never met Ed in person before this. So I knew his name and I saw his picture. Wait. All right.
Collection of bundles. To make up the archive. Okay.
Sure.
All right. Well, oh, yeah. So there's any specific time that means.
Okay. Let me check.
I'm not, I don't.
Are you going to be here?
Yes. I don't know. I look at what's from the
Sure.
state.
And of course with the wax.
I just asked Tom, okay? What Tom say? As long as you don't ask for money, that should be fine.
But
It's a common answer from a
science. Everybody has to be navigating.
And he's happy to push back and discuss with the guy that mentioned taking
Or series, right? The pixels the size of the planet. Right.
At least not excluding the outside partners.
Right.
I'll run the email correctly.
It's not.
Okay,
Good. And you talked to
and I
Tom
haven't talked
Stein
to Tom
about
yet.
getting on the.
We'll try to get that in the agenda.
This one is
Yeah, and
yours.
that's our current thing, right?
Okay, we'll do. Sandy, this is Joe Maffey.
Right, so so far it doesn't sound like it, but yeah.
Heard your name
Our feedback has been.
So Joe is.
Yeah, we want to do the whole mission.
Pretty much taken over.
They'll do it for small
Yes,
sets.
I've been full time on Dawn.
But you know, yes, we want the whole
10
mission.
years or so, but
We don't do it for small sections.
But exactly. I still have the,
Right.
my fingers in the, which is why I'm here.
What you need to do for your. Here's a
It's good to ask if you want to actually know.
But it looks like we've gone so far down the road that actually fixing it.
This is the idea, what do you think?
Well, that's exactly right.
Yes, so for you, just them, right, exactly, and that's also have 46. And what we were hoping to do, where, you know, if there's simultaneous imaging, for example, copy over imaging, and we were hoping we could interpolate between ISS, and turns out that because of the jitters,
You guys.
it really doesn't work.
We have to.
So that was that's actually in our
Yeah.
proposal to do UVIS and series and MIMS as well, but it's not turning out to be very practical.
Peter, contact me.
So yeah, you're right, but those are love the, yes,
We'll
those
get 10 of them on the day.
You know, it's like,
It's like
Starting
the
on
second week of
you know,
July.
like I'm a ring researcher, right? And, you know, like I researched the F ring, right? And a different also of the F ring is the A ring. Oh, absolutely. Right? It's like a wrong ring. Exactly. So that's something that
I think it's mid-July.
Right. And we just don't want everyone to have to
So
do
they
it
do
all.
PR.
And
I'm back, we were talking about having lunch.
Okay, all right. Well, that's
it's up.
All right.
Encouraged to do it. One or two, if you got something simple.
You think we can get it done?
So, give yourself some more.
Margin.
Okay, so that's all.
Yeah. It was nice.
Okay.
Lunchtime is a good time.
Okay.